Hi, Stu Schwartz from MasterMathMentor.com. This is video AB0607 covering two topics. First, the derivative definition, and secondly, differentiation using technology. It covers pages in the AB manual 27 through 31. In video AB05, you were required to learn the formula for the slope of the tangent line to a curve. Let's review that. If we have the function f of x equals x squared minus 3x plus 1, we are interested in the slope of the tangent line to the curve at x is equal to 2. Our formula states that that will equal to f of 2 plus h minus f of 2 all over h. We plug that expression in and we get 2 plus h quantity squared minus 3 times 2 plus h plus 1 minus negative 1 all over h. When we do the expansion, we end up with an expression where the constants 4 cancel. And we have a factorable expression, h times the quantity 1 plus h over h. The h's cancel, and now we examine that expression as h gets close to 0, and we find that the slope of the tangent line at x equals 2 is equal to 1. Similarly, we can find the slope of the tangent line to the function f at x is equal to negative 1. The algebra is shown in the second step. Again, the h's cancel, and we are left with h minus 5 as h gets closer to 0, and we find that the slope of the tangent line to the curve at x equals negative 1 is negative 5. Let's suppose we wanted to find the slope of the tangent line to f at a variety of x values, not just the two that we just did. We would find that we could do it, but the algebra would be pretty much the same. You would end up getting cancellations of the h's, and you would end up with some number that represents the slope of the tangent line. However, this would be quite time-consuming. It is much easier to talk about a formula for the slope of the tangent line. We now define a derivative of a function f of x. This will be the limit as h approaches 0 of f of x plus h minus f of x over h. This is the same formula that we've used for the slope of the tangent line, except now we're using a generic x rather than a specific x value. We will find that this formula could also be written as the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. This is the same formula. Delta x represents the change in x. Notice that in the definition of a derivative, we use the concept of a limit. A derivative is a limit. So we now have eliminated that clunky sort of system where we said as h gets close to 0. Now we have a terminology that we can use. And when we talk about finding the derivative by definition, we're always talking about a limit as h approaches 0 or as delta x approaches 0. Because the concept of a derivative is so important in calculus, we need some notation for it. We'll find that there are several. If the function is written as f of x equals some expression, then the derivative can be written as f prime of x, or simply f prime. If the function is written as y equals some expression, then the derivative can be written as dy dx, or y prime. dy dx is written as dy over dx. Later in the course, we'll find that dy and dx have specific meanings, but for right now, we read it as dy dx. Loosely translated, it means the derivative of y with respect to x. Let's look at an example of this formula. We're given f of x is equal to x squared minus 3x plus 1, the same problem we had above. We're asked to find f prime of x, and also f prime of 2, f prime of 0, and f prime of negative 1. So we will use our derivative formula. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So we first find f of x plus h, which means that we're going to plug x plus h into x in f of x, and then subtract f of x. So we get the limit as h approaches 0 of x plus h quantity squared minus 3 times x plus h plus 1 minus quantity of x squared minus 3x plus 1 all over h. Now there's a lot of expansion that you have to do here. You have to expand the expression, you have to then do some addition and subtraction. You end up getting the limit as h approaches 0 of 2xh plus h squared minus 3h all over h. As we saw before, we can factor out an h upstairs and then cancel it with the h on the bottom. So we end up getting the limit as h approaches 0 of 2x plus h minus 3. And now, using our limit technique that we learned in previous videos, we end up getting 2x minus 3. What does this 2x minus 3 mean? It is a formula for the slope of the tangent line to the curve at any value of x. So if we want f prime of 2, this is simply asking for the slope of the tangent line to f at x equals 2. And by our formula, we get 2 times 2, or 4, minus 3, which is 1, which is the same result that we got in the original problem. F prime of 0 is simply 0 minus 3, which is negative 3. And f prime of negative 1 is simply 2 times negative 1 minus 3, or negative 5. Again, the same result as we got in the problem above. The advantage is that we now have a formula for the slope of the tangent line, and we can use it to find the slope at any value of x. Although not necessary to the problem, we graph the function f of x equals x squared minus 3x plus 1, and we show tangent lines at x is equal to 2, 0, and negative 1. At x is equal to 2, we show the green tangent line, and the slope of that is 1. At 0, x equals 0, we show the tangent line in blue, and the slope of that is negative 3. And finally, at x equals negative 1, we show the tangent line in red, and the slope of that line is negative 5. For this slide, we have left the definition of the derivative of a function f of x on the screen. F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Or we can use the alternative, f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. On all problems on this page, we are given a function and asked to find its derivative. So in problem 2, we're told that f of x is equal to 4x, and therefore f prime of x equals the limit as h approaches 0 of 4 times the quantity x plus h minus 4x over h. The 4x's cancel. We have the limit as h approaches 0 of 4h over h, which is the limit as h approaches 0 of 4. And since there's no h to plug in, we get the limit is 4. That means that the derivative at all values of x on the equation f of x equals 4x is 4. That makes sense as the equation graphs a straight line. And a tangent to a line is the line itself. In this case, a line of slope 4. In problem 3, we changed the notation a little bit. G of x is equal to x squared plus x. So g prime of x will equal the limit. And this time we'll use delta x. As delta x approaches 0 of x plus delta x quantity squared plus delta x minus the quantity x squared plus x. Now, as we saw before, we have to do a lot of expansion and then cancellation. But we are able to factor out a delta x times the quantity 2x plus delta x plus 1 all over delta x. And the delta x's cancel, getting the limit as delta x approaches 0 of 2x plus delta x plus 1. And therefore, the derivative is simply the expression 2x plus 1. In problem 4, f of x is 2x squared minus 5x plus 6. The method is still the same, but the algebra gets a little bit messier. F prime of x is equal to the limit as h approaches 0 of 2 quantity x plus h quantity squared minus 5 quantity x plus h plus 6 minus the quantity 2x squared minus 5x plus 6 all over h. There's expansion to do and then cancellation of terms, but again, we get an expression that is factorable up top. F prime of x equals the limit as h approaches 0 of h times the quantity 4x plus 3h minus 5 all over h. The h's cancel, and we are left with the limit as h approaches 0 of 4x plus 3h minus 5, and that gets us to 4x minus 5. In this case, we're asked for the derivative at 3. So f prime of 3 is simply 4 times 3, or 12 minus 5, which is 7. So the slope of the tangent line to this curve at x equals 3 is 7. In number 5, the algebra gets messier still. We're given the function y equals 4 over x. And since we are told y equals, we'll use the notation for the derivative dy dx. And that will be the limit as h approaches 0 of 4 over x plus h minus 4 over x all over h. This is a complex fraction that we have to clear. And the best way is to multiply by the LCD over itself. So we multiply by x times the quantity x plus h over itself. When we do that, we get the limit as h approaches 0 of 4x minus 4 quantity x plus h all over hx times the quantity x plus h. The numerator becomes negative 4h, and that h will cancel with the h in the denominator. So we get the limit as h approaches 0 of negative 4 times the quantity x times the quantity x plus h. And as h goes to 0, we get our derivative dy dx equals negative 4 over x squared. Note that since this function is not defined at x is equal to 0, it makes sense that the derivative, which is a formula for the slope of the tangent line, would not be defined at x is equal to 0 either. You may be intimidated by all the algebra on this page. Don't be. Taking derivatives is very important in calculus, and we're going to find in video number 8 that there are ways to completely streamline this process, and we can do most of these problems in a matter of seconds. The TI-84 calculator cannot find derivatives of functions. but it can approximate the value of a derivative of a function at a specific value of x. You need to buy more expensive calculators like the TI-89 or TI-Nspire that has a computer algebraic system to actually find the derivative of a function, because these calculators work symbolically. The TI-84 calculator only works numerically, and it uses another formula to approximate the slope of the tangent line to a function at a specific x value. They call it the numerical derivative, and the TI-84 abbreviates this command as nderiv. To use the nderiv function with the TI-84 or comparable calculator, we first put the function we wish to use in y1. So, for example, we would say that y1 is equal to x squared minus 4x plus 1. Now, let's suppose we wanted to find f prime of 3 for that function, meaning that we want the slope of the tangent line to that curve at x is equal to 3. Nderiv is found in Math 8. So you would use the nderiv command and type in nderiv, or Math 8, y1, comma x, comma a. In this case, the a is 3, so you would type in nderiv, y1, comma x, comma 3. The y1 can be found through the y-vars menu, and you could also type the function into the nderiv command. So you could also type in nderiv x squared minus 4x plus 1, comma x, comma 3. No matter which way you do it, you get an answer of 2. So the slope of the tangent line to that function at x is equal to 3 is 2. Example 1 states that f of x equals x to the fourth plus 3x to the third minus 5x squared minus 6x. And we'd like to find f prime of negative 2. We can use our formula, but we're going to have to expand expressions like x plus h to the fourth power, x plus h to the third power, etc. There's going to be a lot of messy algebra in there. However, if we make at y1 equal to the function, then we can just look at nderiv y1, comma x, comma negative 2, and we find that f prime of negative 2 equals 18. Number 2 states that f of x equals e to the negative x minus x. Using our formula involves algebra that is just too complex to easily work with. However, putting the function into y1, we then look at nderiv of y1, comma x, comma negative 1, and we get that the slope of the tangent line to the curve at x equals negative 1 is equal to negative 3.718. Number 5 states that f of x equals sine of 2x plus cosine of x, and we want to find f prime of pi over 2. Again, the formula would be too difficult to use because of the algebra, but looking at nderiv of y1, comma x, comma pi over 2, we get that the slope of the tangent line is negative 3. In this problem, we confirm this graphically. We come up with the equation of the tangent line using the point-slope formula. The point is pi over 2, 0, so our equation is y minus 0 equals negative 3 quantity x minus pi over 2, or y equals negative 3 quantity x minus pi over 2. The graph shows the result, and the red line is tangent to the curve at pi over 2, even though it actually crosses the curve at pi over 2. An interesting result will take place when we place the function in y1 and the numerical derivative into y2. So in this example, we placed f of x equals x squared plus 2x minus 3 in y1. And y2 we define as n deriv y1 comma x at x. This means to take the derivative of y1 with respect to x at values of x. We then create a table using values of x from -3 to 3. And we look at y1 and we look at y2. y1 is the value of the function. y2 is the value of the derivative, which is the slope of the tangent line at that x value. So for instance, f of x passes through the point -3, 0, and the slope of the tangent line to that curve is -4. We then look at the points in the table, x comma y2, -3, -4, -2, -2, -1, 0. And we connect those points and we find that they create a straight line. Now you might wonder, why doesn't this line appear tangent to the curve? Realize that it is not the tangent line to the curve. The y values represents the slope of the tangent line to f of x at each value x. So when x is -3, the slope of the tangent line to the curve is -4. When x is -2, the slope to the tangent line of the curve is -2. If we connect those points, we get a line, and it turns out that the equation of that line is y equals 2x plus 2. That would be the result if we used our f prime of x formula on the expression y equals x squared plus 2x minus 3. The last paragraph on page 30 is important. Please remember that the calculator is only finding derivatives numerically and not symbolically. And since the derivative is a formula for the slope of a tangent line, we're going to learn techniques to find this formula that are much easier than the method we've shown already. So much of the semester is going to be devoted to that need, and the calculator is not much use. But if you need to find the slope of a tangent line at a specific x value, the calculator works very well. And even if your teacher requires you to show work, the calculator can verify what it is that you find by hand. One final statement about the n-deriv function on the calculator. N-deriv is an approximation for the actual derivative. It is not the actual derivative. And while in most cases the accuracy will be very close to the real thing, there are cases where n-deriv will not give an accurate answer. Later in the course, we will show some of them.